Excellent. Okay, so today, well, first off, how'd you guys feel about the last assignment? Alright, because I got a bunch of stuff to pick up from you guys so that we get caught up on the grading and stuff like that. But when you guys start working on the assignment too, the other thing is I have to make sure that I put in, since this was our snow day assignment, I have to go in real quick onto RDS and put these, well the grades are here in, but I have to mark that you did the snow day thing, and so you get either a 1 or a 0 for the snow day, but it doesn't get computed into your grade, okay? You'll see it on the grade sheet, but it's just part of, it's something that their software uses to track certain courses.
Attendance.
Yeah, well, it's basically attendance. I don't know, the attendance thing is down again today, I'm not sure why. Okay, so I'll get some of the grades from you and so on, but I want to talk about this next section that we're doing, which I have been looking forward to since like I found out I was teaching this class, and this is about like some of the physical applications of derivatives. I mean, on section 3.2, we did some derivatives that were done using the hard way, the limit rules, you know, and we were doing them, oh man, the limit as h approaches 0 of that q, that difference formula, that difference ratio, to use the right word, and that was the hard way. And then in section 3.3, we found out that there's all these differentiation rules that are, you know, like that power rule, or the product rule, or the quotient rule. In fact, there's a whole bunch more, but we're not learning them all in one day. Okay, that are good ways to like find the derivatives for simple polynomial type expressions and so on. And it becomes kind of a thing that you can lose track of what any of this is for. What are you actually learning how to solve using calculus? Because that's what's great about calculus, is it's so obviously important once you know what to do with it. And that's what we're doing today, is about what to do with it. Where we're learning about derivatives as like a physical thing, they are the rate of change. And that can be kind of a hard thing to think through until you see some examples of it. I mean, when we are learning about, if we can make some kind of equation that describes something physical, like the position of a car along the racetrack. You know, at time t, the car will be at some spot. So like its position is f of t, where, you know, maybe it's t squared. Okay? I mean, you know, at time t, this is how many meters down the track you are. Because that would be way too simple, right? It would be more complicated, it would have more numbers in it, and so on. But at that time, where the car is. The derivative of position, like this is position. The derivative of position, which in this case would be 2t, is velocity. At any given time t, the speed you're going is the derivative of the equation that describes the position. So if you wanted to know at 10 seconds, at t equals 10 seconds, what your position was, it would be t squared, or 100. So at time t equals 10 seconds, you'd be 100 meters down the track. Not exactly great acceleration. Maybe this is a bicycle or something like that. I don't know. And your velocity at that time would be 2 times t, where t is 10. So it would be 20 meters per second. And for that matter, the second derivative, which in this case would just be derivative of 2t is just 2, is your acceleration. Acceleration. So you are accelerating at a rate, so if your position is in meters and your velocity is in meters per second, your acceleration is in meters per second, or meters per second squared. And suddenly you have all kinds of problems you can solve. And your book wastes no time throwing some at you. Like, I like this one better. Here's the position of a ball. The ball is currently 65 meters above the ground, or 64 feet apparently. Let's use exactly the problem. So at time 0, the ball is at 64 feet above the ground. And then this equation, which they're using s for position, as a function of time, is, and here's the equation. This equation tells you at any given time where the ball is. So just as an example here, at time 1,
the ball would, so at time t equals 1, the ball would be at negative 16 plus 64, which is what, 48 meters, or 48 feet, I guess the problem is in feet. And so at time 1, the ball was 48 feet above the ground. And at time, it works out, let's see where the ball is at time 2. At time 2, let's see, negative 16 times 2 squared minus plus 64 equals 0. So at time 2 seconds, the ball was at height of 0. So this equation describes the height of the ball in feet. But we could take the derivative of this equation and find the velocity of the ball. So the derivative of s as a function of time, where s is position at time t, we just take the derivative. Minus, let's see, 16 times 2 is 32t, because we reduce the power by 1, and then the constant, derivative of the constant is just 0. So this is our velocity in feet per second. So we could plug in this number any place. We want to know the velocity of the ball at time t. How about at time t equals 1? At t equals 1, the velocity then would be negative 32 times t, or negative 32 feet per second. Which is, you know, the same as the slope of the function at that time. Or, let's just say at time 2. At time t equals 2 seconds, the velocity of the ball is negative 32 times 2 equals negative 64 feet per second. Which is going to be the slope of the line as it is tangent to t equals 2. Man, there's all kinds of problems you can solve with this. Notice that these are, strictly speaking, the instantaneous velocity. Instantaneous velocity. They are the velocity at that exact second. At that exact moment, even. In fact, if we had plugged in 1.1 seconds, we'd have gotten a higher velocity, right? I mean, it's literally the velocity at just that exact time. Okay. If we had wanted to have the average velocity, what we would have done is over the period of time. Over the 2 seconds, we changed speed by, we went from 64 meters above the ground to 0 meters above the ground. So it would have been like the change in height over the change in time. We would have said we changed height 64 feet in 2 seconds. Our average speed would have been 32 feet per second. Which, as it happens, 32 feet per second. Which is that, by the way, in this case, happened to be the same speed we were going at in the middle, but it wouldn't have to have been that way. So the average velocity is going to be like, we're just using arithmetic. We're saying over that 2 second period of time, we went from one height to another height. We changed height 64 feet in 2 seconds. So we averaged 32 feet per second. We can also have talked about this in terms of the acceleration of gravity on this ball, or however it's accelerating. Acceleration, I misspelled it. Where that is the second derivative of the position, which in this case is just negative 32. Negative 32t, the derivative of that would just be negative 32. The units are going to be feet per second squared. It has a constant acceleration. Every second, it's getting 32 feet per second faster. Your book does throw out one more vocabulary word. Let me just make sure that's working out here. And that is speed. Just to be clear, if you've not had that in a physics class or something like that, speed is just the absolute velocity, absolute value of velocity. Speed can't be negative. You don't have any negative numbers on your speedometer, right? If you're backing up, well, actually on a car, if you're backing up, they usually don't tell you anything. But speed is, you can have a negative velocity, because you're getting closer to the x-axis or whatever, but you don't have a negative speed. Oh my gosh, there's so many cool things. That's like half of science right there. Everything you're going to ever learn in a physics class is that. It's just different ways of saying it. But we'll get there later in the semester. So you're going to have a whole bunch of these kind of problems here. We're going to be talking about, notice they sometimes actually label velocity as like v of t. Oh, I should erase this stuff so you can see better. So like they're labeling, sometimes they're saying velocity is v of t, and acceleration is a of t. Just notation. Okay? So like velocity as a function of time is just the first derivative of the position with respect to time. And acceleration as a function of time is just the first derivative of the velocity or the second derivative of position. Because the acceleration stuff might not be constant too, although they usually are, the kind of problems you have in this class. Okay. All right. So they then proceed to like, well, here we go. Let's do another one. Using that same information. All right, here's some particle. The position of a particle moving along a coordinate axis. So this is like a particle being accelerated down a magnetic field, or by gravity, or whatever. And it's just being given, here's its position. S as a function of time is t cubed minus 9t squared plus 24t plus 4. Who the hell knows what that is? I mean, they just made the problem up. In physics, there'd be all kinds of numbers there, like your universal constant of gravitation, and your force that you're accelerating it with, and all that kind of good stuff here. And the problem is saying, find the velocity as a function of time. Well, the velocity as a function of time is just the derivative of s with respect to time. And hey, that's one of those ones that's easy. That's just a power rule applied to a polynomial. So let's see. It's going to be, let's see, derivative of t cubed is 3t squared. And then negative 9t squared, that's going to be negative 18t plus 24t is just plus, the derivative, that's just plus 24. And the derivative of plus 4 is 0. So that is all you need right there. Alright? Next, the problem says, at what time is the particle at rest? What do we mean by at rest? At rest means the particle's velocity is 0. So, how are we going to do that? Oh, that's just finding the roots of this, okay? We would just say, that means take this equation for the velocity and set it equal to 0. Which you were great at in algebra and pre-calculus and stuff like that. Where you would take this equation, hey Eric, how would you solve this equation to find the times at which this is going to be equal to 0? What would be your favorite way to do that?
I haven't really looked at it.
Okay, that's a fair enough answer. Does anybody have an answer as to how we're going to do that? How are you going to find the values of t such that 3t squared minus 18t plus 44 is equal to 0? How are you going to find that?
You can factor it.
You could factor it, or you could use a quadratic equation. Either of those would be fine. Okay? I'm not great at factoring, but probably it can be done, right? Probably something like 3t, t, and with a little bit of fussing, we could get this. I would use the quadratic equation because that's just the that's how I roll. Okay? But that would work. On what time intervals is the particle moving from left to right or from right to left? Okay? Moving from left to right. So we have some kind of equation that as a function of time, we have this position, s. So, let's see. How do I want to draw this? I don't like how they said left to right, right to left. Let's call that, how about instead of saying left to right, let's say from down to up. Okay? Just because that would be easier to draw. Let's work with it that way. So here's our function with respect to time. This particle is someplace at any given time, described by this equation. How are we going to figure out when is it going up and when is it going down? Well, you're going to take the derivative, the velocity is equal to this thing, and find out when is it greater than 0, that's when it's moving up. And when is it moving down because its velocity is negative. You already have the times from the previous part where it's at rest, where its velocity is 0. So all you're going to have to do is try some values. Right? You'll have ranges of time. Heavens, let's actually look at the answers. Here's our derivative of the position, in other words, the velocity, and we had that right. Part B, at what time is the particle at rest? The particle's at rest when the velocity is 0, so we just set the velocity function equal to 0, and they factored it. I would have used quadratic equation, but I don't care. And it turns out that there are 2 times where the particle will be at rest, where the velocity at time t equals 2 seconds and time t equals 4 seconds. Those will be 2 times when the slope of the tangent line was equal to 0. Now it says, is the particle moving? The problem said left to right or down to up. So we know its velocity was 0 at time 2 and at time 4. So we would just test and see, is the velocity positive or negative at each of these places? If the velocity is positive, it's going down, up. If the velocity is negative, it's going down. Oh man, these things are all over the place in like Physics 1. These things are all over the place in lots of science classes. Alright. That's a little sketch. I don't love it. Whatever. This isn't the only thing we could be solved using these derivatives for, although changes in position and acceleration and so on are certainly extremely common solutions. I mean, any kind of physics class, any kind of science class is going to need them. Another kind of science that would use them is population change. Where like, if you have some kind of function p that is the population as a function of time, then the rate of population growth for that equation is just the derivative of p. That is what the derivative is it's the rate of change. So the derivative of an equation that describes the population is equal to that. Yeah. I'm trying to think. Yeah. Oh, hold on. Just writing just an example. So yeah, it doesn't really matter what we're talking about in terms of what the population is. Was it in the pre-calculus class or was it in the finite math class last year? Where there were the problems that involved populations of like wolves in a park and bacteria in a petri dish. I think it was pre-calc that had that. And there were a whole bunch of those. Now they didn't get as far as to take the derivative of it, but they had equations that were of the form like the population of this is equal to some number times e to the t or something like that. Now you don't know how to take the derivative of an exponential like e to the t just yet, but when you can, you will have that the derivative of the population explains the rate of change, how the population is growing. Alright, so you'll be doing those guys on there. And in fact, they can do the same sort of game with money. Now they use a little bit different terminology when these are applied to money. So for example, like if you had a function called C, where C is the cost of producing a certain number of items. So C of X is how much it costs to produce X items. So maybe like if each item was it was $12 to produce, then to produce X item costs 12X, then the term they use is marginal cost. The marginal cost is how much it costs to produce 1, and that is the derivative of C. So the marginal cost of these things that we're building is just the derivative of C. Well, wait a minute, the derivative of 12X is just 12. In other words, it costs $12 to make each thing. Which isn't very illuminating until the costs get more complicated.
you know, like maybe it costs you a lot to make a few things, and it costs you less to make more and more of them. Like cars. I was just reading the other day, I don't know if any, I know there's some guys here who like cars. And I was just reading the other day, did you guys see those blog posts that were out there about the car industry in Madagascar? Madagascar has its own car industry, separate from like Ford and Renault and all, things like that. They build cars, small numbers of cars. One of the car manufacturers in Madagascar only produces 12 cars a year. Not 12 models, 12 cars. But they're hoping to ramp it up because while they can produce, once you can, yeah, it costs a lot of money to make 12 cars, your marginal cost is high. If they can make 12,000 cars, their marginal costs are going to get lower. It'll be cheaper to keep making more and more cars, right? Once they have all the dies made and the production facilities and so on. So their cost per car maybe has something in it like square root of x. Okay? Where the bigger and bigger x gets, it doesn't get faster. It does, you know, the first couple cars, there's a big marginal cost, but the marginal cost gets smaller the farther out they go and now build more and more cars. Alright, anyway, and I'll leave it to you guys to find. There's similar vocabulary words that you'll need for some of the problems, like the revenue from selling X items, then the marginal revenue, which is the revenue for selling each item, comes to the derivative of revenue, and so on. Profit, which is the difference between revenue and cost, then the marginal profit, the profit you make off of each item comes to this derivative of R minus derivative of C, and so on. This is cool stuff. We're just beginning to see all the kinds of things you can do with this. Now, where did that go? Maybe I was looking ahead. Hold on. Yeah, I don't want to talk about that just yet. Okay, so you know what? I can probably get it from there easier. Hold on. So let me get you guys the assignment. Alright. Derivatives is a rate of change. Page 273. And forward. It is 151 to 165i. Oh man, I love this stuff. There are so many cool things we can do with this about figuring out the winds, temperature change. Oh, I'm thinking about meteorology. I gotta stop doing that. Alright, I'll let you guys start working on that, and I gotta get these things entered for the snow day stuff, and you guys will have whatever questions you have.